With this difficult chapter, you really need to be working hard on the exercises, struggling with them, and hopefully coming through the other side. Although some of you are really doing fantastic, the rest of us have to work. Okay, so we've spoken about functions a couple of times now, and as an engineer, you can think about them as expressing a relationship between variables. So, for example, the area of a square and its side length. You can think about the relationship between them as a function. Now, it should be written well here. So if you want to say that area depends on side length, you can write A is equal to A of S. Now that's exactly like f of x. It's to say that area is a function of S, area depends on side length. Now it isn't that the side length causes the area. What it really means is for each value of the side length, there is a single value of the area. And these are graphs of functions that you know, the normal differentiation that you did last semester would have been covering. So for each value, each side length, there is, so you, and then you can graph them. I think we mentioned this earlier. So you graph all the points of the form input, output, and you take all of those infinitely many points and you have the graph of the function. So other examples, height of a projectile depends on how much time it has elapsed. So you're watching a rocket as it starts, that's time equal to 0, and then at every single time there's a single height associated with that. The yearly sales depend on the number of years. Now that's where you're getting away really from the amount of time that the product has been on sale doesn't cause the sales, but for every number of years there is a sales figure. Whereas the next one kind of feels more a bit like the time causing the temperature to increase or whatever. So the temperature of a component depends on the time it has been used. We've got example of beams where all these functions or all these variables are functions of the distance along the beam. So we've got the load per unit length, how far along the beam at each point there'll be a certain load per unit length, there'll be a certain shear force, certain bending moment, certain slope, and certain deflection. Speed of an object depends on time, acceleration depends on time, and we've got more of these. Okay. The current in a circuit of fixed resistance depends on voltage. The population of bacteria depends on time. Force in a spring depends on extension. So these are all functions of a single variable. So the volume of a cylinder of fixed radius depends on height, and the volume of a cylinder of fixed height depends on radius. So I think the examples, page 30, or the 13th example is an important one. So these actually naturally, volume really isn't a function of a single variable height or a single variable radius. It's a function of two variables, radius and height. And we've stressed it a number of times in this module that a function doesn't have to take a number as an input. And in fact, it could take a pair of numbers. Now matrices can take a pair of numbers, 2 by 2 matrices, but matrices are very special functions. They're linear. This is the other thing about the functions we're going to study here is it's going to be a pair of numbers in or a list of numbers in, it's going to be one number out. Whereas matrices weren't always like that. Okay, so functions of several variables. So consider the bending moment on a light beam that spans 6 meters subject to a constant UDL load. Looks something like this. And as we said, for each distance along the curve, there's a single point. So at x equal to 2, the bending moment is m of 2 is some specific value. So many functions in engineering, physics, maths tie together more than two variables. For example, the bending moment on a square plate depends on two variables. Like if you want to describe where you are on a two-dimensional plate, you have an x coordinate and a y coordinate. And so you want to say what is the bending moment there, you're actually putting in a pair of numbers and you're getting out one number. So here we see, in this case, the bending moment is a function of two variables. Then questions like how the bending moment varies as we change x and y. Okay, it's easy to see. But what we want to do, take stuff from single variable calculus, really we're talking about what you did last semester, and use it to study functions of more than one variable. Now, usually we're going to look at functions of two variables, and usually they're going to be abstract, but not always. So z, so usually we're going to be writing z is a function of x and y, and the idea is you put two numbers in, a pair of numbers x and y in, you get a single number z out. So here's some examples. The area of a rectangle depends naturally on two variables, width and length. For beams, actually, I said above that they depend on distance, but actually you can change the beam, you can change the cross-sectional area of the beam or the material. So all those things really depend. And you could also you could change the span. So you could have that these things are a function of four variables. The current in a circuit actually depends on resistance and voltage. And the example we spoke about, the volume of a cylinder, depends on radius and height. Now you wouldn't say it depends on pi because pi is a constant. Okay. Graphically, these things, like, remember how we said we plot a function of a single variable? You plot all the points of the form input output. Now if you look at the points of the form input output, say for current, so the input, say for example, could be voltage 10, resistance 5, and the output then would be the current is 2. Now, how do you plot that? Well, of course, you identify this. There's a fancy word here. You could say it's kind of isomorphic to 10, 5, 2. So I'm saying input, output, because actually you can define the graph of like even matrix functions, but like you can't actually draw a picture of them, but you can study them. But anyway, again, beside the point. But this one is quite easy. If the input is two numbers and the output is one number, just put the three numbers together like that. And 10, 5, 2 is just a point in space. So the graph of a function of two variables is three-dimensional. So for example, here if I said that maybe this was x equal to 1, y equal to 2, go to the point above that, you'd have the point 1, 2, and then put 1, 2 into the function, which here is x squared plus y squared. You get out 1 squared plus 2 squared. 1 plus 4 is 5. And so that's a point on the curve. And then, you know, you could, there's different things we can study. Okay. So another point there is 1, 1, 2, which might be something like that. And all the points of the form input, output make up the graph. Right, so in terms of motivation, so now we're not going to actually do much with it. Well, we will actually today, well, whenever you watch it, we will in fact do a little bit of this in the next section, but eventually what you'll be looking at is maximizing functions of several variables. So just an example, a kind of a silly example, but an example nonetheless. If you have a box without a lid and you've got so much cardboard, and if you want to maximize the volume given that you've only got 12 meters squared of cardboard, how would you do that? And you can imagine it kind of comes into the design of cans and different designs, you know, like with a can, say beans, you want to maximize the volume for a given area, or maybe more realistically, minimize the area for the volume so that you're using a minimum amount of material. And you can use what we'll be studying, partial differentiation, to maximize this. The answer, by the way, is 4. You've got other problems. Rectangular building is designed to minimize heat loss. East and west walls have a certain design, north and south, certain design, floor, certain design, roof, certain design. Each wall must be at least 30 meters long. The height must be at least 4 meters, and the volume must be exactly this. Find the dimensions that minimize the heat loss. So you can use what we're going to do in this section to study such problems. Okay, so the idea of a partial derivative, so you can do a kind of very kind of abstract way, which is kind of hard to understand, just using symbols, but I think it is possible to understand this. And when you are kind of lost, just to go back to what we're going to discuss here. Okay, so we have a mountain in front of us. Now, what I want you to imagine is if you think about a mountain, it's supposed to be a mountain, and suppose you have, now I know Earth is not flat, but imagine it is here. Okay, so a mountain, and in fact the surface of the Earth, well, the surface of the Earth is a function of two variables. Now it's a bit weird because the inputs and the outputs, longitude and latitude, they're points on a sphere, which is actually two-dimensional. The surface of the sphere is two-dimensional and it's not flat. But anyway, your two numbers in, your latitude and longitude, number out is your height at that point. So you do have a function of a single variable, two variables. And so the question I'm asking is, if you move in the x direction, say we're going to move in the negative x direction, the way I've drawn this. Suppose you climb up the mountain like that. Right, so there's the picture in the middle, and there's a kind of schematic of it. Now the way I've drawn it is it's minus x into the page. I have to be careful because, actually I'm going to adjust this, right, but what I can't do is I can't just make the bottom thing to be minus x because of the stuff to do with vectors. You have to keep an orientation between x and y. So actually I'm going to change this around a little bit. I'm going to call this x, and then this can be minus y. I might say that's very fussy, but so be it. So we'll draw it like this. So as you travel in the x direction, what is the slope? Now the big story about when you travel in the x direction, so we're looking at how does the height change. Along that path, the y coordinate doesn't actually change. Like say for example, the y coordinate, now the way this picture is drawn, it'd be over there, right? But so let's say the y is equal to minus 2, and if we drew it over there, say the y is equal to 2. I appreciate that's a bit confusing. I just have to do things kind of correctly. So if you walk along either the path on the left or the path on the right, y is constant, doesn't change. So for example, if you what direction you're sitting, and if you're not sitting exactly north, south, east or west, just face that way for a moment. And if you walk, like say, where am I facing now? I think I'm facing west. If I walk directly west, I don't move in the north or south direction at all. So my north-south coordinate is a constant. Similarly, if I'm facing north, and if I travel exactly due north, I don't move in the east or west direction. So what we're going to study is how things change. In this case, z, the height, if I change one of the variables but keep the other one constant. And this is the essence of what's called partial differentiation. The idea is that you just differentiate with respect to x. You look at how x changes, but you keep everything else, y in particular, the same. So if we look at this from side on, so this is supposed to be either of those pictures. If you're looking at the rate of change, or not even that, if you take a slice out of the mountain, it's a function of a single variable, and we know how to differentiate them. So, not sure what I'm going to write here. In general, we have that z is equal to a function of x and y, but if y is fixed, then we can talk about, I'm going to say, I have to be careful what I write here. So if f of xb is a function of x alone, I can differentiate it. Now I can write dz dx, y is equal to constant, is just the normal derivative of x of b. Okay, so just to differentiate it as normal, I'm saying y is equal to some constant b. We've just written this down. So the rate of change of f of xy with respect to x at a point when y is fixed is, in other words, if I want to find the slope on the mountain, I just imagine slicing the mountain and just doing a normal differentiation, but I have to keep y constant. Okay, so I think probably what we need to do here now is do some examples. So, now one of the things is, so we're always saying, oh, we're going to fix the y value. So here, for example, we're going to do that. Now, we're going to write down y equal to 2, but usually it's not going to be, y is just going to be left as y, and it'll be understood as constant. So here I'm going to let z is equal to f of x2, and f of x2, so at that fixed y equal to 2, that's actually just a function of x. And I'm going to write it in this weird way. I'm going to write it as x cubed plus, now the y cubed is 2 cubed, and I'm going to write that first. I don't have to do that, but I'm going to do it. I'm going to take it nice and slow at the start. Times x squared, and then the minus 2y cubed is minus twice 2 cubed. So all I've done here is I've said, okay, if y is fixed at 2, and I substituted in y equal to 2. Now I didn't evaluate anything, because eventually I'm not going to be subbing in a value of 2, so there's no point evaluating it. So now let's go off and differentiate this thing. Now what we're going to differentiate is the g. The g dx is equal to. So differentiate term by term, fixing constants. You might have seen me earlier on. So for example, a lot of you would be trained to differentiate 4x cubed, and you think about the 3 maybe multiplying the 4 outside, maybe 3 by 4x squared, maybe that's what, oh, terrible notation, 3 by 4x squared, is that what you do? It gives you the right answer, but when it comes to this level, it's not actually a very good way of doing it. What you're much better off doing is, if you're differentiating a constant times a function, to fix the constant and then differentiate the function. Now it gives you the same answer, but it's better for this section and arguably sections on, well, this section anyway. So let's go. So derivative of x cubed, and okay, a sum of terms is no problem, you differentiate term by term. The derivative of x cubed is 3x squared. Now the next thing, I'm going to fix the constant 2 cubed, okay, and then I'm going to differentiate x squared. So derivative of x squared is 2x. And then, well, what's the derivative of the thing at the end? Well, if y is fixed, that's just a constant, so the derivative of a constant is 0. And I'll tidy it up to a small degree, 3x squared plus 2 cubed times 2x. I'm not going to tidy it further. Now, what that means is we could do the same thing with, you don't have to say y equal to 2, you could do y equal to b. So you could say that, say z is equal to a function of x and b, but we're not specifying, so we're saying y is a constant b, but we're not specifying that constant. This one I'm going to call h of x, because it's a slightly different function. I could call it, maybe call this thing g sub 2, and this g sub b, but maybe that's kind of complicating. Well, actually, you know what, I think it's actually better. So I'll call this g sub 2. It means fix the function, fix y equal to 2, and look at this function of x. Now we're going to do it with b. So fix y equal to b, and now you have a function of x alone. So this will be x cubed plus, so I got y cubed, that's now b cubed, times x squared, and then minus twice b cubed. I'm just putting in y equal to b. And now we'll differentiate this gb with respect to x, and it works pretty much the same. It didn't matter that y was equal to 2. It works basically the same. So derivative of x cubed is 3x squared. I'm going to fix the constant b cubed, and the derivative of x squared is 2x. And then the derivative, well, the last thing there is b is a constant. It's not a variable. We're not specifying what it is, but it is a constant. And so the derivative of a constant is 0. And we can tidy it up a little bit, 3x squared plus maybe we could go with 2b cubed x or something like that. Okay, so generally we won't say y is equal to 2, we won't say y is equal to b, we're just going to say y is equal to y, it's fixed. We're not specifying what it is, but it is fixed. So in general what we're going to do is say if z is equal to a function of x and y, and y is fixed, so then we define g, say y, it's not the best notation, as f of x was kind of a bit nonsense really, so y fixed. Then we can define the partial derivative of, now I could say z or f, it doesn't really matter. That's like doing dy dx or df dx, it's the same thing. I'm going to partial, maybe I'll do partial z. Now we won't really be able to do the f dash notation, because if you say f dashed, is it differentiated with respect to x or y, you got a bit of a problem there. So this is the derivative, the normal derivative of gy of x. Or you could write that as the derivative of the original function, but just that you're specifying that y is constant or fixed. Okay, and this is what's called the partial derivative. So you let x change, but you don't let y change. And really the thing in the background is you're fixing y and you're actually studying one of these slices and you're differentiating that. So similar story, you have differentiate with respect to y. Okay, let's go. So now just initially I'm going to write the thing in different forms, one for differentiating with respect to x and one for differentiating with respect to y, just to make it clear what I'm doing, but after a while we'll stop this. So this is in fact equal. So with respect to x, this is the way I'm going to look at it. X squared is variable plus. Now for x times y to the 5, the y to the 5 is a constant, so I'm going to put that out in front, times x. And then for the next thing, what are the constants? So I'm going to, with respect to x, so 6 is a constant, and if I'm differentiating with respect to x, y is constant, times x cubed. So when you get the hang of it, you won't be writing, well, you probably won't be writing this at all if you kind of follow what I'm doing. And then y to the 4 is constant. So that's what I'm going to differentiate with respect to x. Now differentiating with respect to y, the x's are constant. So the very first x squared is a constant, plus a constant x times y to the 5. And then take away a constant 6x cubed times y plus y to the 4. So on the top one, they're both the same thing. I mean, changing the order of multiplication, these things are just numbers. It doesn't make any difference. But on the top one, I'm treating y constant. I'm thinking of it, I will be thinking of it as constant. And this one I'm thinking as x constant. So the top one really is like a function of x and the bottom one is like a function of y. And so I can differentiate the top with respect to x and I can differentiate the bottom with respect to y. But now this isn't like, there's no implicit differentiation or parametric differentiation. This is really differentiating with respect to x is on the same level as differentiating with respect to y because you've got two variables. Okay, so let's actually write down some maths. Now I won't, no, I'm fine. So the derivative of, now I can say f, I could say the derivative of f respect to x. Use this funny symbol. Now, if you ask what it is, look, it's called partial. It's mostly just a maths thing. The partial symbol. So partial, say z, partial x. So we're going to differentiate this thing on top. So it's a sum of terms, so you do term by term fixing constants. The derivative of x squared is 2x. Now, when we're differentiating y to the 5 times x, we'll fix the constant y to the 5, and the derivative of x with respect to x is 1. And the next bit, we have a constant times x cubed, fix the constant minus 6y, and the derivative of x cubed with respect to x is 3x squared. And with respect to x, the derivative of y to the 4 is just the derivative of a constant is 0. Now there's different things about derivative of constant times something and derivative of constant plus something. This would have been covered 2 weeks ago. So we'll tidy this up. So I have 2x plus y to the 5 minus, say 6 by 3 is 18 by x squared by y. So that's the derivative with respect to x. Now if I differentiate the bottom thing with respect to y, so I'm going back to where I started and I'm treating the x as a constant. So this we call the partial derivative of z with respect to y. So x squared with respect to y is just a constant. Derivative of a constant on its own is 0. Now we have a constant times y to the 5. So fix the constant x And what's the derivative of y to the 5? 5y to the 4. We're going to, on the next term, fix the constant minus 6x cubed. And what's the derivative of y with respect to y? 1. And then we have the derivative of y to the 4, which is 4y cubed. And we can tidy that up. X times 5 times y to the 4. 5x y to the 4. Minus 6x cubed times 1. Plus 4y squared. So there are different notations. So for the derivative of a function partially with respect to x, you'll see all these different notations. Well, I'd probably mostly just focus on these ones, to be honest with you. Okay, so to compute partial derivatives, yeah, it's written there. Now all the ordinary rules of differentiation still apply, like product rules, chain rules, quotient rules, etc. Okay, I think we'll do one more example and then we can we'll drive on. So we have a function here of x and y. Find the derivative of f with respect to x, derivative of f with respect to y at a certain point, and interpret them. So we'll do this. Well, this one's kind of easy because we don't have any constant multiples of x and y together. So let's see the derivative of z. Well, here now there's no z. I probably shouldn't say z. Although often you'll say dy dx when there's no explicit y, but let's keep it like this. So differentiating with respect to x. So 4 is a constant, derivative of constant 4 is 0. Minus the derivative of x squared is minus 2x. And with respect to x, y is a constant. So if y is fixed, so is y squared, so is minus 2y squared. So the derivative of minus 2y squared on its own is 0. Now if it was 2y squared times x squared, you'd fix the constant and differentiate. So this, we'll just put it in here. So the derivative, and this is just normal differentiation, of constant plus a function. Sure, we'll just use x squared for argument there, x to the 4, 7 for argument's sake. So derivative of a constant plus x to the 7 is 0 plus the derivative 7x to the 6. But the derivative of a constant times x to the 7 is a different fish. In that one, you fix the constant and then you differentiate. And if you want to see why that's the case and why the first thing doesn't contradict the second thing, go off and differentiate this using the product rule, noting that the derivative of a constant is indeed 0. Okay, so back to where we were. So this is the derivative with respect to x, and it's saying evaluate this at the point 1, 1. Now that means x equal to 1, y equal to 1. Now there's no x's involved here, so this is just minus 2. Now we'll get back to that in a moment. Now also partially differentiate with respect to y. So this time x is constant. So the derivative of a constant 4 is 0. The derivative of minus x squared. Now with respect to y, x is constant. So x squared is constant, so the derivative of minus x squared is 0. And on the last one, I'm going to fix the constant minus 2. And the derivative of y squared with respect to y is 2y. Nothing like 2y dy dx. It's not. We're not saying that y is a function of x. X and y are both variables in their own right. So this is minus 4y. And if I evaluate this at 1, 1, I get minus 4. So now we have to interpret these as slopes. So remember the derivative, normal derivative gives you the slope. If we go back a few pages, so if you're differentiating with respect to x, you're kind of doing the slice and you're looking in the x direction. What is the slope at the point in the x direction? And similar for the y. So now if I can, oh, God knows which is which here. Which one do we think is x and which one do we think is y? Well, I actually think the picture just looks a little wrong, so I'm going to kind of cheat. So I'm going to pick this to be the x-axis and this to be the y-axis. Well, that's what I said it should be. Okay, but anyway, so we've got a point 1, 1. And, well, we can substitute in that into the function. You get 4 minus 1 squared minus 2 by 1 squared. That sounds like 4 minus 1 minus 2, which is 1. So that's the point we're at. Now let's look in the x direction. So the x direction is this direction. Actually, this works. Throw that. That's the x direction. See, so this is like differentiating with respect to x. And then we also have this direction is differentiating with respect to y. Sorry, I'm going to have to just finish up this one fairly quickly now. So if we look at the slope in the x direction, we saw that it was minus 2. So the slope of this line, now it's hard to see, but the idea is that if you go across 1 in the x, you'll go down 2 in the y. So the slope of this is minus 2, and the slope of this line is minus 4. Okay.